Welcome to Mastering E. Today we're going to be looking at Chapter 1, Problems 1.1 through 1.9. So Problem 1 asks us how much charge is represented by these number of electrons. So all these problems should be fairly similar and pretty simple. So basically we're going to be using the fact that our charge is going to be equal to the number of electrons multiplied by the Coulomb charge of one electron. And the Coulomb charge of one electron is going to be negative 1.602 times 10 to the negative 19 coulombs. So for A, the implementation for this would look like 6.482 times 10 to the 17, and then we're going to multiply this by this charge of a single electron. And if we multiply this out, put this in our calculator, I don't think this would be very fun to do in your head, although you can if you really want to. Anyways, just writing the answer out, it'll be about negative 103.84, and that's going to be in microcoulombs. And the reason why I did microcoulombs here is that I think it just looks better. That's really the only reason why you need to convert it into microcoulombs, or if the problem told you. So let's go into B. It's going to be the exact same process. And in fact, it's going to be the exact same process for all of these. So what we could do here is just write out how many electrons are actually going to be counted, and then we're going to just multiply it by C. Since we already know what C is, and it's going to be in coulombs, we can just say, maybe you could store this as like a value in your calculator because it could be useful. So our C is going to be this value over here. So the charge of one electron. So if we multiply this by the charge of the electron, it's going to be negative 198.65, and then that's going to be in microcoulombs. Same thing for C. We have 2.46 times 10 to the 19 multiplied by the charge of electron is going to equal, this one we don't have to convert into microcoulombs, big enough, so 3.941 coulombs. And then for D, we're going to have 1.628 times 10 to the 20, and that is going to be in coulombs. So that is just going to be equal to, wow, negative 26.08 coulombs. So these are the answers you should have gotten if you plug this into your calculator correct. Again, I would store this as a value in your calculator. Could be useful, especially if you're in an electrical class like this. So moving on to problem 2, we can look at problem 2 and see that it asks us to determine the current flowing through an element of the charge flow, and then it's going to give us each of these equations. Now, we know from earlier that the current in an element is going to be equal to the derivative of the charge in the element with respect to time. And as you can see here, we do have time variables all over the place. So this is definitely going to be the equation you want to use. How's this going to look? Well, we know just from our simple calculus class, A is going to be equal to 3 milliamps. And that's another thing. When we derive this is going to be in coulombs, and this is going to be in seconds. So as you see, coulombs a second, that is going to be equal to amps. So that's the units right there. So for B, we're going to just have the derivative of 8 times t to the power of 2, which is going to just be 16t from power rule. And then this is going to be added with the derivative of 4t, which is just going to be 4 minus 0, and that's just going to be in amps. And we aren't giving a specific time here, so having our answer as equation isn't a big deal. For C, we know that when we take the derivative of an exponential, it's just going to be the chain rule there. So we're just going to have negative e. Getting ahead of myself. So we're going to have negative 3 e to the negative t. Again, keeping this the same. And then derivative of 5 times e to the negative 2t is going to be equal to, well, this is a plus, or this is a minus right here, so we're going to turn it into a plus when we bring that negative down, and it's going to be 10 e to the negative 2t. And since that's going to be in nanocoulombs, we're going to have nanoamps. And then for D, we have our sine function. We're going to have this in the inside here, so we're going to multiply this in the inside by this on the outside, which is just going to be, wow, okay, it's going to be 1200. It's going to be 1200 pi, and that's going to be a cosine now, and then we're going to keep the inside the same, so 120 pi t, and that's going to be in pico amps. So again, basic, I believe that's chain rule right there. Almost forgetting the names. Once you do derivatives so much, you forget the actual terminology, and you just gotta do it. Now this is going to be a little bit more annoying, as we all love. This is going to be a little bit of a product rule here, so you know that one, unfortunately. So we're going to take our first term. Let's take the derivative of that. This is going to be negative 80 e to the 4t, and then that's going to be multiplied by our second term, unchanged, so cosine 50t, and this is going to be added with 20 e to the negative 4t, and then actually we'll turn this 20 into 20 times 50, which is going to equal 1000 e to the negative 4t, and then cosine will turn into negative sine. So get this sine checked right here, negative sine 50t. And we could simplify this, just taking out negatives, taking out the e to the negative 4t, and then we're going to have 80 cosine 50t plus 1000 sine 50. We could have taken out more, but we'll just leave the answer like that. So that's going to be our answers for question number 2. Moving on to question number 3, I'm going to say find the charge Q of t flowing through a device if the current is, and we're given all the currents. Well, now, since we were just finding what the current was from given the charge, and now we found the charge given the current, and we took the derivative up here, obviously we want to take the integral, or the antiderivative, here. So we can state that the charge as a function of time is going to be equal to, we could just say this is going to be equal to the integral, and we could say, you know, if we really wanted to, times 0 times 1, but this is going to be I of t, so our current, and then with respect to dt. So we weren't really given any times here, that's fine. Oh, and I almost forgot, because we don't want a plus c, we can just add our q at time 0. This is because we are given this in each one of the problems. You may or may not be given this in each one of your problems, but if it's from this book, it'll likely give it to you. So let's look at the first one. We have 3 amps. So 3 amps. So for A, we're just going to have the integral of 3 dt plus our q naught, or our q at time 0, which is just 1, and that's in coulombs. So from here, what we can do is we can just integrate. So we know the antiderivative of this is just going to be 3t, and then it's going to be plus 1, and then that is just going to be all in coulombs. So B is going to be a very similar process here. We're going to say this is going to be the integral of 2t plus 5, and right here our q of 0 is nothing, so we don't even have to write it. So right here we know the integral of this, so this first term is just going to be t squared plus 5t, and that's just going to be in millicoulombs. For C, want to just take the integral of 20 cosine 10t plus pi over 6 dt plus our 2 micro coulombs over here. What we could do here is, I mean, we could basically see that this is going to be a u sub. So if we want to, we could just say this is going to be u, and we can just divide this by 10 then, because we know when we take the derivative of this part, it's just going to be 10. So we're going to have 2, and then the derivative of cosine, which is going to be sine, and then we can just replace right back that u to be 10t plus pi over 6, and then plus 2, and that is going to be in microcoulombs. If that didn't make any sense, definitely want to review your u substitution, because that is an extremely easy u sub right there. And if you really see this and you're on a test and you need time, really just divide this outer part by this number and then just take the antiderivative of what's on the outside and you'll be good. Okay, so last but not least, we have D. We'll just put this one over here. To the integral of 10 e to the negative 30t sine 40t. And then plus our q0, that's nothing. So, okay, so first, this is going to be a little bit more complex of an integral right here. However, we want to recognize it in its standard integral form. So for this one, we can use integration by parts, or just recognize it as a standard integral of the form that when we have an exponential here and then a sine function here, we're just going to have this equal to e a t over a squared plus b squared multiplied by a, and then our sine of bt minus b cosine bt. And this makes sense, right? So obviously this looks like a product rule kind of form where we have the two t's multiplied by each other, but not in the easiest way. So we'd have to use integration by parts, but I think everyone hates integration by parts. So that's exactly what we're not going to do. And we're just going to plug in the values here, man. So really this is just going to be e to the, and our a is going to be this, and our b is going to be this. So yeah, I mean, this is just going to be negative 30t over, well, 30 squared is going to be 900 plus 40 squared, which is going to be 1600. So that's just going to be 2500 down here. And then it's going to be multiplied by negative 30 sine. That's going to be 40t. And then we're going to add that with negative 40, and then cosine 40t. So yeah, if this looked like an extremely hard integral, which it would be definitely a little tedious to do, I would recommend looking at this form and just knowing this, just so if you see something like this, you can easily integrate it and don't even have to think about integration by parts. So for problem 1.4, this is a current of 7.4 amps flows through a conductor. Calculate how much charge passes through any cross section of the conductor in 20 seconds. Now, this might be kind of worded in a way where you think like, oh, this might be a little bit more complex, right? I can't just use a standard formula here, but actually you can. So all this is just going to be asking us for is the current, is the charge rather. So the charge is going to be equal to I of t. I should say times t, not of t. So all we have to do for this problem is notice that our current is 7.4 amps and our time is 20 seconds. And in problems like these, that's going to be the values you're going to be looking at, right? All this other fluff, you really don't care a whole lot of, especially if you're going to be going fast on a test. You want to look at your current, which is going to be, that 7.4 amps, and then we're just going to multiply that by our 20 seconds. So this is going to be, and of course, if we wanted to look at the units here, current is going to be coulombs a second, and then time is obviously in seconds. So these are going to cross out, and it's going to be coulombs. So to make sure your units work out like that. But anyways, we're going to multiply these, and then obviously this is just going to be 148 coulombs. This is going to be the answer for 1.4. Then 1.5 says determine the total charge transfer over the time interval 0 to 10 seconds when I of t is equal to a half t amps. And now we can use the same formula as we were using earlier, where our charge is going to be equal to the integral of this time. We actually have a time interval, so we're going to have 0 to 10, and that's going to be of a half t, and that's in amps, but when we integrate this, it's going to be in coulombs. So we have the dt. So integration here should be pretty easy. We're going to have 1/4 t squared for the interval 0 to 10. And if we do this out, what we see is going to be 100 divided by 4, so it's 25 minus 0, and this is just going to be equal to 25 coulombs. So that's how fast some of these problems can be done. You just got to know your formulas and just basically plug and chug from there. So for problem 1.6, well, it's asking us, or it's telling us that the charge entering a certain element is shown in this figure, and we're supposed to find the current at each one of these times. For A, we're going to be looking at 1 millisecond, so t is equal to 1 millisecond. And using our formulas from before, we can just see that I is going to be equal to dq with respect to time. So we could use this formula, right? But all this is really telling us is basically the change in charge over the change in time, right? So from this, since this is not a weird like parabola curve or anything like that, we can just recognize that the peak here is going to be, it's going to go from 0 to 30, so 30 minus 0, which is just going to be 30, and it's going to go to 0 minus 2, or 2 minus 0, which is just 2, and then this is going to just be 15. Oh, that is an 8. It's impressive. I don't even know how I did that, but this is going to just be 15 amps. And then for B, it says t equals 6, and this is just a flat line, and we know that derivatives of unchanging things, like a constant, are just 0. So our answers so far are 15 amps and 0 amps. 0 amps for time equals 6 milliseconds. And for C, at time equals 10 milliseconds, we can just recognize here, this is again going to be this change formula. And this change formula this time, though, is going to be in the opposite direction. So we have 0 minus 30 instead of the 30 minus 0. That's going to be over. That's going to be over 12 minus 8. So this is going to be negative 30 over 4. And that is going to be equal to negative 7.5 amps. So the charge is going to be flowing in the opposite direction here. Okay, so for problem 1.7, the charge is flowing in a wire, and it's plotted here, and it wants us to sketch the corresponding current. Okay, so for this problem, what we need to recognize is what we're actually doing here. So I'm going to set up a little bit of a piecewise function here. So our I is going to be equal to, as we can see here, these are going to be 50 divided by 2 is just going to be 25, and then same thing here. And we can just say that, so for this interval right here, we're going to have 25 amps, and this is going to be from 0 t to 2. And then we're going to have negative 25 amps from 2t all the way to 6. And then from there, we're going to have 25 amps. This is going to be from 6 to t8. I don't know, I keep forgetting the sign here. Okay, so to plot this out, we are just going to have our y-axis here, our x-axis here. We actually want to extend this down because we know we're going to have some negatives, and then negative 25, and then we're just going to say 25 up here. And this is going to be I of t, These are going to be in amps. Okay, so from here, we'll each one of these, let's just see, this is the 2, this is the 4, this is the 6, and this is the 8. So we're going to have 25 amps until 2, and then we're going to drop to 0. And then it's going to be a kind of a discontinuous function. We could just say it kind of looks like this. It goes to about 6 right here. And then it's going to pick back up at 6. And then we're going to go to 8 as well. And since we don't know what happens after that, we'll just close it off here. So your graph should somewhat look like this. This is what a function would look like. And I didn't really define my axis as too well. This is just going to be time here. But yeah, I mean, this is as simple as it gets. This is just going to be the simple sketch of the curve here for problem 1.7. Okay, so for problem 1.8, it says the current flowing past a point in a device is shown in this figure, and it tells us to calculate the total charge through the point. Now, what we can see here is that we have this point right up here for our current, and this for our time right here, obviously, but this is going to extend across the top here. And you know, we could take the integral of the I and to get our charge, right? But we can do this without taking any integrals, really. And that is just going to be basically splitting this graph up into 2 parts. So from 0 to 1 right here, so our time there, we're just going to have this 10. So this 10 times our 1 for our 1 second. And then this is going to be, since we have a triangle here, we need to divide this by 2, because, you know, 10 times 1 is going to give us the entire area of this, but we just want to find the area under the curve, and the area under the curve here just happens to be a triangle, so we can just divide this by 2, and then we also want to add in this area right here, and this is going to be really easy, because again, this is just going to be this little this partition here is going to be 1, and then it's going to be multiplied by the height, which is 10, and then it's not going to be divided by anything because it's the entire thing. So we can just notice this is going to be 5 plus 10, so this is going to be 15. And since the time is in milliseconds and the amperage is in milliseconds, we're going to have 10 times the negative 3 times another 10 times the negative 3, which is going to equal 10 times the negative 6. And this is going to be for our units, right? And this is going to be in microcoulombs. So this is going to be in microcoulombs. So definitely don't mix up your units here. If you just wrote milliamps, millicoulombs rather, you'd be way off by a factor of like literally 1,000. So definitely make sure you're paying attention to the units. For the last problem of the day, we're going to be looking at problem 1.9, and it says the current through an element is shown down here. Determine the total charge that passes through an element at each one of these times. So we're just going to look at, for time equals 1 second, we can recognize that we have our amps up here, seconds down here, so we're going to have our current, the integral of our current with respect to time, which is going to equal the charge, right? So here we can see that from 0 to 1, which is what we're going to be asked to integrate here, we're just going to have 10 seconds here. Or sorry, not seconds, 10 amps. And this is going to be the derivative, or the it's going to be the integral with respect to t. And we know this is just going to be equal to 10t 0 to 1, which is just going to be equal to 10. And that's going to be in coulombs. So that was simple enough. Now for B, we can just call this A. For B, we're going to do I'd say similar process. However, we really kind of want to maybe take apart this problem and recognize that we have a square here, we have a rectangle here, another square here, and then a triangle here, right? So what we want to do for this one, instead of actually taking the integral, because it would be kind of weird if we took an integral when this function's obviously not like nice, what we want to do is just take the sum of all the areas of these, right? So we're going to have down here we're going to have 2 times 5, right? And that's going to be added with, okay, we got 1 times 5 here, and it's going to be added with, we'll leave this to last, a 1 times 5 again, and then adding this, so it's going to be 1 times 5 again, but since this part's a triangle, here I'll just mark the places we've done, but since this is the triangle, we have to divide it by 2. Okay, so yeah, if we just do all the math here, simple math, 10 plus 5, 15 plus 5, 20 plus 2.5 is going to be equal to 22.5 cool. So from there, we're going to look at C. So we could really just take this 22.5 and then add another, we know the value of 1 square, we've done it so much, is going to be equal to 5. So it's going to be 27.5, and then the area of one of these triangles is going to be 5 over 2, which is 2.5. So that's just going to be 30. So we're going to have, we could write this out, but 22.5 plus 2.5 plus 5, that's just going to be equal to 30. That's going to be 30 coulombs. So a little bit of a longer video here today. We got through a lot of these simple problems and definitely the fundamentals for the rest of this course. So yeah, if you have any questions, if you think I made any mistakes, make sure to drop a comment down below. And if you want to see the rest of chapter 1, click on screen now for the full playlist. Thanks for watching.